Hello and welcome to this second presentation of 3 on cyber threat management. My name is Philip King Wilson. I'm a visiting scholar at the University of South Florida, Department of Information Systems Decision Sciences. In this second presentation, we'll work through a practical example of how we can create a network value at risk. So that is to say, looking at what are the threats posed to the organization from the network and how can we create a financial value to enable risk managers to understand how best to mitigate or eliminate such risks. This is a strategic decision, and we covered that in part 1 of the series of presentations.
So we're talking here about network risks that can impact upon any organization, resulting in data theft, financial losses, and how to measure and manage these particular risks. There is a far higher visibility of cyber threat management in terms of publicity, but although the high-profile hacks and targeted attacks bring a broader discussion about the subject, the reality is that it is, in many respects, a management trend. Now, this may seem a strange thing to say, but by that I mean the numerous external suppliers such as consultancies, specialist IT hardware providers, all latch on to the one thing that's being viewed as critical and urgent. By contrast, there are very valid reasons as to why a corporation would want to create and run a cyber threat management program in order to derive a network value at risk for themselves, perhaps in conjunction with external suppliers. Firstly, every organization should have undertaken a business continuity planning exercise, and cyber threat management falls within that domain because they're interlinked. Secondly, businesses are migrating operations to the cloud, and cyber threat management will be entering a new phase. For example, the United Nations has just issued an invitation to tender for the creation of cloud-based intrusion detection systems, since that organization will be using the cloud on an increasing basis. Commercial and military organizations will therefore increase dependence upon externally controlled platforms for their operations, and cyber threat management will have an even greater prioritization. Thirdly, and this has been going on for well over a decade and a half now, and we covered it in part 1, businesses are trying to integrate IT into business processes in order to eliminate operational overheads and to reduce transaction costs in order to maintain or increase profit and productivity. Fourthly, risk management can, as we saw in part 1, increase capital efficiency through reducing risk capital reserves, better allocation of capital to risk mitigation, and in capital cost lowering through their being perceived by ratings agencies that an organization has a lower risk exposure than competitors. Fifthly, and coupled to all the above, risk management is a fundamental activity in business, and since cyber threat management is one component within operational risk management, it's logical to address such threats in the same manner as other risks posed to the business. Sixth, a relatively new topic for management and commenced really as a result of the fallout to businesses of the 9/11 attacks, which exposed which businesses were capable of operating in the aftermath of those events and which could not. An example here would be Fedwire, which still operated, but it was at a 40% reduced capacity, and that cost the government $46 billion in discount fees to the banks because they took a large hit as a result of the reduced capacity to trade. And finally, regulatory and legal compliance. In some sectors, it's necessary either to allocate a fixed percentage to risk as a general risk pool, or to measure each individual risk and allocate an amount to cover the risk. So if we take again the banking sector, by measuring every operational risk, including IT risks and therefore cyber threats, banks can allocate a risk amount to it within their reserves. If they don't measure and value, then they're obliged to hold a fixed percentage of the risk-weighted assets of between 3 and 10%, depending upon the capitalization level of a bank. Clearly, if this is greater than the risk capital required for a measured and valued risk, then the bank frees up capital in the latter case. Allied to the regulatory requirements, though, are the increasing number of laws that impact upon most sectors. From data protection, which impacts on every business, to anti-money laundering laws, to healthcare patient data crossing even state borders with varying requirements, There is now effectively a dictate requiring every organisation to assess and value their network risk, because the cost of non-compliance can damage an organisation to a very great extent, or even require it to cease operations until compliance is achieved. When we talk about network risk valuation, we're talking about a number of different risks posed, but primarily we're talking about traffic inbound from the internet towards a company's security perimeter. Here we're using Wireshark just as an example to capture traffic on a Wi-Fi network, for example, in order to analyze it. Typically, a network topology will have a router, various packet filters and firewalls, and then the traffic is routed within the security perimeter according to the LAN and the business requirements. In our model for creating a network value at risk, we use a network tap to copy traffic that's inbound to a company from the internet. This traffic is analyzed and threats identified and categorized as well as counted. This in turn feeds a threat assessment system that takes company-specific data into the model.
In this demonstration model, it's important to understand that here we're only looking at the inbound traffic from the internet towards the security perimeter. From a risk management perspective and for legal and regulatory compliance, obviously we should be having exactly the same for the outflowing traffic from the organisation's network back out to the internet. There are a number of international and national regulatory laws that are becoming increasingly stringent, with prosecutions up to $250,000 in fines and up to 25 years imprisonment for example, spreading computer viruses and worms knowingly.
A passive device is used for network traffic capture, whereby all the traffic is copied across and stored. It's worth noting that the packets are not inspected in terms of their payload, thereby overcoming privacy and other issues if this is being undertaken on behalf of a customer, for example. Don't forget too that traffic outbound can and should be copied and analysed in order to both identify threats being generated inside the company or being redistributed as a result of a virus or a worm, for example, having got through the security perimeter. When we talk about the captured traffic being analysed, we mean that the traffic is fed into an analysis engine which determines the volume, type, target, frequency and period of every threat ID. The threat IDs are within the headers, as we just said, and these are known from the general threat databases used by hardware and software manufacturers for their security appliances and software.
As times change and technology evolves, it becomes increasingly easy to capture network traffic and analyse it. How cheaply? Well, this is a Raspberry Pi. It costs $50 in the United States, £40 in the UK, and this is actually a computer. We also need a USB additional port in order to capture the traffic. That costs $15. A cheap couple of cables and a cheap switch which has enablement for mirroring traffic. You can also use a very old hub which just repeats all the traffic to all the ports. You can find those typically online for around $20. So for a total of around $75, any small business owner could actually monitor what's going on incoming from the traffic towards his small network and going out from the company to the internet to ensure regulatory compliance.
So if we take a look at an actual piece of traffic that's been copied and analysed here, we can see a number of data references. Firstly, we can see that there is a threat ID, and this is the ID issued by the generalized threat database we just referred to, and not one generated by us. Secondly, the category is termed indiscriminate because this is not a virus or worm that's a focused attack. In this particular case, this is just a worm or virus that's been mass distributed. The target of this type of attack is not known, so it's not a type that is seeking to target a security hole or a system vulnerability like the SQL Slammer attack type, for example. The severity score is listed as 7, which means that it has the capability of doing quite severe damage should it get through the security perimeter of the organization. We can also see that there is a timestamp operation and that the observations in this case are run constantly but batched into weekly counts. For this particular virus, the number of times it's seen by the traffic analysis engine per hour is given, with the volume being fairly constant except for two couples of periods in this screenshot of between 11 o'clock and 11:59 with 5,400 odd occurrences and a high of 1,210 in the same time on a Tuesday, which would seem to indicate this is an automated type of dispersion attack. Now we have the traffic and its analysis, we can move on to a high-level overview of the model we use for this example of network value at risk modeling. In our model there are inputs, processes and outputs. The traffic that's been analysed provides the input from the threat analysis engine database, and this will give us the level and types of threat activity. However, we also need to be able to predict ahead of time what the activity levels for this type of threat will be in the future period. If we don't do this, then the calculation for the network value at risk will be out of date before anyone gets to see it. Forensic accounting and similar types of analysis are termed autopsy risk analysis, in that the negative event has actually happened, and now there is a need to work through all the events and stages to understand how it happened and how to prevent it in the future. A prime example of this type of risk management is in the aviation sector. For us though, cyber threat management needs to be predictive and not with hindsight, and so we need to be able to extrapolate from the data in order to predict future activity. A useful spin-off of this is that whilst the security perimeter is able to handle the current volumes of threats, an early indication of a growth that may overwhelm security will enable the organization to be able to forecast what will be needed in the future. This may amount to little more than load balancing changes, but it could also be to ensure capital allocations by senior management are going to be sufficient for an increased IT security spend. Another input is the IT systems, and this feeds a system risk calculation engine. What this does is link to the next inputs, those of business process value at risk calculator. The end combination of inputs and the calculation engine then outputs a business network value at risk. So taking the model and drilling down a little, we can see that there is a need to map between systems and processes. In part 1 we covered business process analysis and mapping, and here we're taking that one stage further and combining business processes with their relationship and their interdependencies with systems and categories. In this example we're talking about system categories. So a system could be SQL database, and the category could be that it runs on HP, Proliant, Intel, 2.5 GHz, 64 gig servers. However, we can also say in another example that the system is SAP and the category is a geographical location, such as St. Pete or downtown Tampa, etc.
So from this example model, it's clear to see that there is a requirement to map between processes and systems in order to understand the dependencies of IT and functions. If you haven't yet seen how this is done, which was covered in presentation number 1, now would be a good time to do that. In the meantime, we'll carry on and we'll look through a practical demonstration of how we can map systems, processes, categories and their interdependencies in deriving a value at risk for a network.
So here we can use the software tool to map the relationships between processes, with examples here being generic ones, systems, which could be at the application level even, and categories, which here are geographies. And then we can now start linking the various processes to the various systems, with the processes obviously using some, all, or none of the systems, depending upon the function served by each of the systems. And then we can do the same exercise to link between the systems and the various categories listed here. So we end up with a mapping diagram something like this, but in far greater detail. In this simple example, we have the processes listed as those typical in a commercial institution, such as point of sales, human resources, banking, etc., and the systems, as we described before, as being large-scale descriptions. The categories here are geographies. The degree of granularity required by the organization can be served by tools such as these by enabling a process systems mapping tool to be separate from the rest of the software application. This means, as in this case, it could be emailed to every person in the company, a request made for them to individually map which systems and applications they use, and then imported back into the main application to give a total organizational network value at risk to the nth degree if that was required.
Here we're looking at a corporation's systems, processes and categories, the relationships between them and the mapping of the interdependencies. However, if ever there was a great example of a reason why the cyber threat management environment is so dynamic and difficult to plot, it's the Stuxnet attack on the Siemens software systems from 2009 to 2011. This was originally created by American and Israeli computer scientists intended to target Iranian nuclear power plants. Why was it such a game changer? Well, it's quite simple. It was the first worm that actually targeted industrial process control systems with a rootkit to enable a targeted attack. This rendered a lot of the prior knowledge with regards to how computer viruses and worms actually operate completely redundant, and a rethinking of the whole environment too.
And we can see how this would affect the operating environment we all take for granted in terms of utilities, core products and services. Previously, these types of operations were closed-circuit types of networked processes and control systems. However, the ability to roll out systems and controls using IP-based networks meant that costs fell, and the ability to control multiple locations centrally streamlined operations, reducing overheads. As soon as these SCADA systems became IP-based, with remote access and control, then they became vulnerable in the same way as any other IP-based network is. The previous means of taking such processes down would be to physically impose damage on them in some manner, whereas now attackers have a variety of means to achieve their objective remotely. Examples here would be a Stuxnet type of attack or an electromagnetic pulse attack and so forth. The end result of this is a reprioritization of what needs protecting in an internet world. National governments are looking deeply into all aspects of national infrastructure protection in the light of the 9/11 attacks, and we can rest assured that every major network attack such as the Target credit card hardware hack will refocus and redouble their efforts.
Now we're going to go deeper into the actual modelling of cyber threats posed to an organisation, and we're going to do this by doing a software walkthrough to understand how can we actually create a network value at risk. Now the task of actually creating a network value at risk doesn't fall to one particular team within an organisation. Usually it will involve IT departments, business continuity planning departments, and the risk management department, the operational risk management department. And then there are different factors which can impact on how we can best mitigate the risk exposure to an organisation. There are the various factors we can take a look at and see what influences they have on the overall network value at risk.
The methodology we are going to use requires us to firstly address cyber threats experienced by the company. This is the copied data that's then analysed. The attributes per attack type give us the target of the attack and enables us to assign a percentage of the total attacks to each target. When we move down to the number of new viruses predicted in a future period, the model we're using in this instance takes the current attack types, looks at the number of new viruses in the wild published by various organisations such as SANS or WildList, and then extrapolates forward the anticipated number of new viruses, and then this is used within the balance of the model. In this colour-coded screenshot we can see there are three types of data used: observed threats, external information and user-defined. and this is then used to generate the fourth set, which is predicted threats. If you look at the left hand column, you can clearly see that this is the data generated from the threat analysis system using the copied network traffic. We can then turn our attention to the second part of the modelling methodology, which is for systems and categories. The practitioner determines the downtime arising from each threat where there is no mitigation, and then calculates the same again for if there is a mitigation action taken. We can then calculate, based upon the number of occurrences, what the total downtime of a system will be as a result of a successful cyber threat penetrating the perimeter defences. When we talk about mitigation actions, there is a very simple methodology attached in many instances. An example here would be to simply look at the number of mitigation options, calculate the probable or actual reduction in the value at risk as a result of implementing it, calculate the residual value at risk for the company, and list the cost of the mitigation action. The risk manager will then align the residual value at risk to the risk appetite of the organisation. We start by taking the baseline risk exposure and creating a new mitigation option to see the effect on the organisation's overall network risk exposure. And we do that by inputting changes to the existing infrastructure and or other types of threats. We input first the cost of implementing this particular mitigation action, and then we can go into the company's infrastructure map by opening the existing process systems and categories mappings file. If we then change how the company's operations function by removing the usage of perhaps a system by a process or a couple of systems by a couple of different locations, we can then see how these changes have influenced the company's network value at risk. The cost is obviously displayed as the cost of the mitigation action so far, so the overall effect is a cost only at this particular stage. If we now though add a few physical attacks or use this component as a proxy for another non-network enabled attack, we can see how this too, in conjunction with our other changes, affects the network risk exposure, if at all. And finally we can see here that the effect is a reduction of around $202,000, and so this option is less effective than the mitigation option numbers 2 or 3, and therefore would not be adopted as the first mitigation option action.
There are of course non-network types of attack and threat that still can undermine a corporate network and therefore impact on its network value at risk. We'll take a look at a few simple examples in a moment, but it's worth noting that the algorithm that we're using is very flexible, although it is an example one, and we can use part of the algorithm as a proxy for modelling these physical threats, we'll label them. My personal experience of these types of threat posed to a network are, for example, in the Netherlands, every data center manager is fearful of flooding because the majority of the country lies below sea level. In Kuwait, they're fearful of terrorist attacks on data centers, from terrorist bombs or insider threats even. And the third one I've come up across has been a major Belgian telecommunications corporation who established a business continuity plan, developed backup data centers, but were fearful of leakage of incorrect data from one client to another over a period of time. So let's take a look at how we can actually use the algorithm to model these physical threats.
Returning to non-network threats, so far in this screen you'll see there's a data center fire, vandalism, insider attack, bomb alert, earthquake, and we're going to add flooding, and in Florida with a severity of 5 and with a frequency of 4 per decade and with a uniform profile and within the Eastern time zone. In the case of modelling network value at risk, we can do the same exercise by changing certain parameters and then seeing what the outcome is, with all this being based upon the same methodology that we've just seen. For the third part of the network valuation model methodology, we now take the data for processes and link them to the systems and categories data. This is where the organization's business continuity program couples with the cyber threat management program, in that the data gained by the business continuity team can now be used as accurate inputs into the application for the values of process downtimes. The output of the system is displayed as a bar chart series for the organization's network value at risk, and the display enables easy identification of those processes which require the most attention in terms of security. What's very useful about using tools such as this is the need to communicate effectively at many levels within an organization and to gain a clear understanding of the problem, the solutions, and the costs of acting to resolve the problem. And this type of tool does that very effectively.
If you think back to the first presentation, one of the key points with regard to risk management in general is the requirement to continually identify, assess, prioritize and limit threats posed to an organization. This is pretty much the same as you would do for business continuity planning. However, in a cyber threat environment, it tends to be far more dynamic, although it does play a part within the overall business continuity planning process. For the next slides that I'm going to show, it'll show a historical trend line for a threat. This isn't a typical one. The software system has actually picked up the start date of the demonstration. So normally you would have a profile line, much the same as a bell curve, for example, showing risks over a period of time and the mitigation options that reduces it in line with the organization's risk appetite. So let's have a look.
Here we have a graph with the axis of network risk value together with the prediction date on the other axis. Normally this application would have been running over a period of time and you would have been able to see the trend line. At the top left you can see the prediction rate and the network risk exposure for the company, and at the bottom left the summary information from the system to enable risk managers to base their programs upon. One major question that's frequently posed to risk managers and other associated personnel is why one particular type of algorithm is used to manage risk and why not another. We'll look at the use of a different algorithm for the same purpose in the next presentation. However, in many cases the simple truth of the matter is the one used must suit several purposes. It has to deliver the information senior management need in order to understand the risk exposure of their organization. It needs to increasingly deliver the information required by regulators and enforcement agencies that the organization is in full compliance with a multitude of laws. In this particular case, the use of a number of methodologies can lead to what's sometimes called the black box syndrome. This is where the risks posed are so complex that they require incredibly complex algorithmic models to define the value at risk. The infamous example we could use here is the financial markets crash of 2007 to 2008, whereby the regulators simply didn't understand the products and their complexity, and they couldn't understand the systemic risks that had actually been created. When I sometimes answer this question as to algorithmic applicability, the audience is sometimes shocked when I explain to them that the Risk Management Committee, when deciding their modelling, will resolve the choice by answering a simple question in turn: will the regulators believe us? In the case of our example of cyber threat algorithmic modelling here, we've also been able to use part of it as a proxy for the inclusion of cyber threats. Perhaps the best explanation of modelling and risk management is to think of it in the same manner as management accounting has been. Using management accounting methods, a company can determine the cost of production, but not with a vast array of accuracy in many instances. However, before management accounting, companies frequently had absolutely no idea what their cost drivers were within their businesses, even remotely. The origin of that practice has evolved into various types of management accounting philosophies such as transfer pricing and resource consumption accounting. So if we don't start the practice of cyber threat management, we'll never evolve and develop it, and at this stage of maturity of both cyber threats and cyber risk management, it's better to start to understand the managed threats using an IT security framework as well as a risk management one.
Coming up in the third and final part of this series on cyber threat management, we'll be looking at alternative algorithms and how they could be used or their applicability to modelling cyber threats. We'll be taking a look at the cloud computing environment and the emerging threat landscape within that, risk financing as a mitigation option, and why this last option may actually be limited over a period of time to risk managers.